Did you know that we pay better attention if we can see the person that's speaking? So that's why I'm showing up and presenting this to you. This is the in-class assignment where I asked you to try out Euler's method on using two different initial conditions for this particular differential equation. I'm going to now go through the slides so that you can see. I'm not going to go through this part of it until the very end. I'll show you an Excel file. So I'm going to go through the part that has to do with what we call differential inequalities. And on the board, I'd shown you that if I plug in t equals 1 into this, which is the upper right-hand limit, because I really just want to integrate this from 0 to 1, if I plug in t equals 1, then I have that the right-hand side of my differential equation, which I don't want to integrate because it's yucky, and I don't really know how to integrate that. It's bounded above by 1 plus y squared. And on the other side, if I plug in the lowest value for t, I get that it's bounded below by just y squared. So basically, here's t squared as a function, and it's that curve between 0 is bounded between 0 and 1 inside the interval t equals 0 to 1. So that's kind of what I'm doing, just bounding it below and above. There's a very important theorem that says if you have a differential equation like that's bounded and sandwiched like this between two different things, then my solution that I don't even know how to find in closed form has to be bounded between the solutions of y squared and 1 plus y squared, these two differential equations to the left and right on this interval 0 to 1. Let me push this over a little bit. Let's see. You can see better? Okay, so here. So this is just what I said. That means the solution to y prime equals t squared plus y squared, it actually is between the solution to y prime equals y squared and y prime equals 1 plus y squared. Why does that matter? It matters because I'm able to actually solve these two by separation of variables. I do know how to solve these two. And again, this is old school math because today I would just take t squared plus y squared and numerically integrate it, run cutout order 4, or stick it on Mathematica. But in the old days, you really didn't know your solution if your code was correct or not. So in that case, you have these two bounded solutions. You have your solution sandwiched in between the solutions of these two things that you can solve by hand, and you can check your work by making sure that your numerical solution, which you set for that order, is between these two things. Okay, so how do I do this? Well, first I'm going to solve y prime equals y squared, which is my lower bound. So I actually have to find the solution. And I did so by separation of variables. I can send these notes out to you. This is not a lecture on separation of variables, but you can do this, hopefully, because you will need to do this on the t. Likewise, so what I know is that my lower solution, my solution is bounded below by minus 1 plus t plus c. I can solve for that initial condition using the initial condition for the c. Again, this is old school, so I'm not going to belabor it. We've done this several times. And you see that the solution is c is 1, and so that this is your lower bound of your function. Likewise, you can do the same thing for the upper bound. You might not remember this, but the fact that I remember this means that I've used it again and again, that the antiderivative of 1 plus y squared is arctan y. And then you solve for y, since it's an arctan, you hit both sides with a tan, and you get this guy, get rid of the initial condition, and so forth. Not going to go into that. It's Jedi math junk, so you probably have done this before, hopefully. If not, I'll send you the slides. So that's my upper bound, tan plus p plus pi over 4. So let's look at first the numerical solution. If I use 0.01 as my step size, and I just run Euler's, I did this on Excel, I ended up with 90.755 as the right-hand side. Let's scoot over here to let's move this over so you can see what happens when I use 0.5 instead. Surprisingly, it's not like the other ones because I get 2.75 as my value at t equals 1. So I get really different things when I change the step size. And that's not what you found before. So why is that? Well, let's look at these solutions. Tangent has an asymptote. If you remember, it looks kind of like a cubic, like a thing. So I'm not going to graph them for you, but this thing has an asymptote. Over here, at t equals minus 1, I also have an asymptote. My guess is, then, that my thing in the center, the solution to t squared plus y squared, probably also has an asymptote. So that's probably why I'm getting the problems I'm getting, because my function that I'm solving for numerically is not well defined, and probably there's an issue at time equals 1. I might have made a minus sign error, not sure. You can correct me in the comments if I did, but that's what I'm seeing. What I would probably do if I didn't have, I would actually numerically use a calculator and actually find the values at 1 for the lower bound and upper bound and see what's going on and see what it looks like. And so that'll give me kind of a better marker of what's going on at the endpoints. All right, hope that was clear. We're going to give you something similar on the t. Enjoy.